Hi everyone, welcome to the seminar today. I am Beth Mashesky. I'll be your moderator for today. We will be holding all questions until the end, but you can type in your questions at any time in the questions box, and at the end we will get to your question. And I'll turn it over to Mike to introduce our speaker.
Welcome. I'm Mike Springman. I'm manager of the Institutional Water Treatment within the Technical Assistance Program at Illinois Sustainable Technology Center. This is a first in what we hope will become a series of webinars by IWT on water using systems. IWT has been able to service its customers for 70 years because of the dedication of its employees. I'd like to take this time to thank the IWT crew, Jeremy Overman, Jennifer Tapuinga, Brenda Huey, and Angela Diascro for their hard work and for making me look good. So if you work around or maintain water systems such as boilers, chillers, and cooling towers, you probably realize what complex systems they are. I see them as kind of like pets. If you take care of them, they can be your friend, lick your face, greet you at the door. But if you ignore them and don't take care of them, they become ill and throw up on your rug. In this IWT series, we hope to address specific common issues within these systems and provide insight on causes and effects and treatments. In this first webinar, Jeremy Overman, senior field chemist at IWT, is going to discuss efficiency of heating and cooling systems and the negative effects of corrosion, mineral scale, and biological fouling on system efficiency. So let's see what Jeremy has for us.
All right, thank you, Mike, for that introduction. I am senior, but I don't have much gray hair, so just to let you know. So thank you for choosing to attend this webinar. There will be time at the end of the presentation for you to ask questions, so save them until the end. To begin, consider what are some of the main factors affecting the cost of operating heating and cooling systems. First of all, there's heat transfer. Heat transfer is the name of the game when it comes to heating and cooling. This directly and greatly affects the energy efficiency of the system. Maintenance and repair are also large costs. Equipment life and replacement costs are also significant. And finally, there are the water and sewer utility costs and the cost of water treatment chemicals. If water treatment in your system is poor, you will have corrosion, bacteria, and biological growths, and mineral scale, and the result will be higher operating costs. All these problems significantly reduce heat transfer and increase the amount of money spent on energy. They reduce the life of the equipment, and they also increase maintenance, cleaning, and the associated labor costs. Another result of poor water treatment is operating the system with higher blowdown or bleed than would be possible with good water treatment. This applies to steam boilers and to cooling towers. The end effect is more money spent on water, sewer, and treatment chemicals, and more money spent on energy in the case of a boiler if there is no heat recovery system for the blowdown water. First, we will look at steam boiler systems. Here's a large water tube boiler. And here are a couple of small fire tube package boilers. Poor treatment can cause scale deposits. This significantly reduces heat transfer. Just 1/16 of an inch of scale on boiler tubes decreases the efficiency by 4 to 11%. 1/8 of an inch of scale causes up to 18% loss of efficiency. The amount of loss depends on the type of scale formed because some are more insulating than others. When scale becomes thick, a tube will overheat and can rupture. And scale increases the cleaning, maintenance, and labor costs for removing the scale. This slide shows the effects of scale and other deposits on heat transfer. On the left side of the screen is a clean boiler tube. Heat transfers efficiently through the steel wall of the tube to heat the water inside to 500 degrees Fahrenheit. On the right is a tube with a coating of scale on the water side. In order to heat the water to 500 degrees, a higher temperature is needed on the fire side. This higher temperature requires more energy, and then more energy is lost when the exhaust travels out through the chimney. Most institutional and smaller industrial boilers do not have economizers. Also, the higher temperature weakens the steel of the boiler tube, and if it rises high enough, the tube will rupture. Here are some tubes from a fire tube boiler coated with calcium scale deposits. Now I'll give you a review of the water cycle in a steam boiler. On the lower left side of the screen is the makeup water. This is typically city water that has been softened to remove calcium and magnesium. The makeup water enters the feed water tank, where it is combined with the liquid condensate returned from the steam system. The feed water then enters the boiler. Pure water evaporates and leaves the boiler as steam. The water remaining in the boiler becomes more concentrated with dissolved solids. The steam then travels through the steam lines, condenses into liquid water to release heat, which heats a building or an industrial process, and then this liquid condensate returns to the feed water tank. Some water is always lost from the steam and condensate system due to leaks. Therefore, more makeup water is needed to keep the boiler from running dry. In this cycle, the water in the boiler becomes more and more concentrated with dissolved solids over time, and eventually needs to be bled or blown down to keep the water from becoming so concentrated that mineral deposits form inside the boiler and other problems occur which produce impure steam. The chemistry of the water in the boiler determines how much water needs to be bled to prevent scale and other problems. Cycles of concentration is an important concept, so I'll describe that. It refers to the number of times the dissolved solids in the feed water are concentrated in the boiler. The conductivity and often the chloride test can be used to determine this number. For example, if the feed water has a conductivity of 100 microsiemens and the boiler water is measured and found to be 3,000 microsiemens, then cycles of concentration in the boiler is 3,000 divided by 100, which is 30. For efficient operation, the cycles of concentration should be more than 40, and the higher the better. Otherwise, the possibility of increasing the cycles of concentration should be investigated. The percent blowdown is calculated directly from the cycles of concentration. For example, if a boiler is running at 10 cycles, then the blowdown rate will be 100 divided by 10, which is 10%. If water chemistry changes are made to allow the boiler to run at 40 cycles, then the blowdown decreases to 2.5%. Blowdown sends water and treatment chemicals down the drain. It also means fuel lost. The heat energy in the boiler water is lost down the drain. If boiler water treatment or control are poor, often the blowdown can be reduced. The result is you will get higher cycles of concentration, energy and fuel savings because less water is blown down, lower treatment chemical use, and lower water use. Often the best way to increase cycles of concentration is to install a reverse osmosis system, which will supply very clean makeup water to the boiler. Each unit in this picture produces 4 to 5 gallons per minute of very clean permeate water. Reverse osmosis removes 95 to 98% of the dissolved solids in the sourced water. This very clean water typically allows you to run a boiler at 50 to 150 cycles of concentration, depending on various boiler system factors. This can reduce blowdown up to 70% and significantly decreases boiler energy use, typically by 5% or even more depending on how thick the original scale was in the boiler. You will use 50 to 90% less treatment chemicals. The boiler will remain much cleaner, and the clean reverse osmosis water can even remove existing scale in many cases. Another benefit is that the condensate will be less corrosive and can become more pure if previously there was a boiler water carryover problem. Reverse osmosis can be economical if you currently have poor quality feed water, such as a conductivity over 100 microsiemens. If your system has a high makeup rate, typically greater than 20%, and if you have a boiler that is 350 horsepower or greater, these are all things to look for an economical use of RO. The economics must be determined on a case-by-case basis. If reverse osmosis is determined to be economical, the payback period is typically around 1 year, but sometimes up to 2 years. Next, we will look at cooling towers and evaporative condensers. If these systems have poor water treatment, you will get scale deposits, corrosion, bacteria, algae and biofilms, and possibly the bacteria that causes Legionnaire's disease. Scale in a cooling tower system decreases the energy efficiency of the tower and the chiller. Just 1/32 of an inch of scale on the condenser tubes of a chiller will reduce efficiency by 9%. 1/16 of an inch of scale will cause a 14% reduction. Your maintenance and cleaning costs will increase due to the need to remove the scale deposits. Here's the picture of the plastic fill in an extremely scaled cooling tower. Here's another severely scaled tower. It has basically become a limestone factory, and scale has blocked off much of the air passages in the tower fill. Here are some chiller condenser tubes with a coating of scale. Again, the scale is insulating and reduces heat transfer. Corrosion causes deposits that reduce tower and chiller efficiency. It also reduces the life of the chiller and cooling tower. It greatly increases the difficulty of removing bacteria and biofilms, as they can live on the surface and inside the corrosion deposits. Here is a corroded evaporating condenser due to inadequate treatment of the system water. Bacteria cause biofilms to form on chiller tubes and other surfaces. Biofilms greatly reduce heat transfer. A 1/16 inch of film can reduce efficiency of a chiller by 35%. Corrosion can occur and become severe underneath the biofilm. This reduces the life of equipment and increases maintenance and repair costs. Bacteria in a cooling tower can cause Legionnaire's disease. This is a severe and sometimes deadly pneumonia caused by inhaling droplets of water containing the Legionella bacteria. Biofilms encourage the growth of Legionella and can protect them from chlorine and other biocides. Here's a picture of some bacterial slime growing in a cooling tower. This is cooling tower fill, which has an extreme biological growth problem. Towers in this condition greatly increase the risk of Legionnaire's disease and most likely contain high concentrations of the bacteria. This is an electron micrograph of the Legionella bacteria. This table shows the effect of cycles of concentration on water use in a cooling tower that evaporates 5,000 gallons of water. As cycles of concentration are increased, the amount of blowdown is decreased, and total water use decreases. The upper limit of cycles of concentration for a specific tower is determined by the water chemistry and is usually due to the formation of calcium scale or other mineral deposits. There are diminishing returns above 6 or 7 cycles of concentration. Therefore, the typical goal is to operate a tower at 4 to 6 cycles of concentration, or sometimes at 5 to 7. This chart represents one 250-ton cooling tower operating at full load for about 11 hours. This table shows how cycles of concentration affects chemical use. The middle column is pounds of chemical added per 1,000 gallons of water used. Operating a tower at higher cycles generally uses less treatment chemical because less chemical is lost through blowdown. And again, the returns diminish after about 6 or 7 cycles of concentration. Improving water treatment can reduce energy use. For example, consider one 500-ton chiller with 1/16 inch of scale. Removing the scale and keeping the system clean would save almost $11,000 per year on energy costs. This example does not include energy savings from operating a cleaner cooling tower. If cycles of concentration are increased through better water treatment, then water, sewer, and treatment chemical costs are reduced. Good water treatment also reduces maintenance costs, prolongs the life of the equipment, and reduces the risk of Legionnaire's disease. Next, we will look at closed-loop heating and cooling systems. Closed-loop systems are filled with water or glycol solutions, and ideally lose less than 5% of system volume per year. Older systems are more likely to have larger leaks. These closed systems transfer heat to or from various types of equipment to provide heating or cooling. Common examples are medium temperature water, high temperature water, chilled water, and ground source geothermal systems. Here's a pump circulating water in a medium temperature water closed loop heating system. Here are some very large chillers. The chiller is the main component in a chilled water system. Problems typically found in poorly treated closed loops include corrosion, system leaks, bacteria, and fungi. Bacteria can produce ammonia, which is very corrosive to copper pipe. Glycol in the system can decompose over time. Bacteria can feed on glycol when the concentration falls below 20%. Decomposition and/or bacteria convert the glycol into acids, which cause a low pH and a very corrosive solution. Here's a severely corroded closed system pipe, probably from a chilled water system. Here's a closed loop heating system with severely corroded copper pipe that also has a number of leaks. Now I'll describe the institutional water treatment program and how we can help you in your facility. The program began in 1949. We have 69 years of experience in water treatment, service, and consulting. We have treated institutional and industrial heating, cooling, and potable water systems. We have also done work at a number of U.S. military installations. We have conducted numerous research projects on corrosion, lead and copper control, scale, cooling towers, potable water, monitoring technologies, chemical treatment blends, and various gadgets. Many gadgets take the form of a magnet that the seller claims will solve all of your problems and scale, all of your corrosion and scale problems if you simply strap it to a pipe. All these types of gadgets that we have tested have not performed at all as claimed. Currently, we serve 120 facilities in Illinois, including prisons, mental health centers, universities, and some high-rise buildings. IWT saves the state millions of dollars each year in energy, water, and treatment chemicals, maintenance, and equipment replacement costs. We can also save money for private companies. We have evaluated heating and cooling system treatment programs, provided treatment consulting, and evaluated cooling tower treatment technologies. Here are our main services. We can monitor corrosion in systems at your facility. We can perform unbiased lab analyses of water, glycol, corrosion, and deposit samples. We can provide ongoing unbiased water treatment service and consulting for systems at your facility, which include regular on-site visits and testing. And we can perform an audit of your current systems as an unbiased third party and look for opportunities to save energy, water, and chemical treatment use. For on-site corrosion testing, we use standard test methods and metal specimens. Mild steel and copper are the most commonly tested metals. However, other metals can also be tested. Specimens are installed in the system, exposed for 3 to 12 months, and then removed. Our lab processes them to determine weight loss of the metal, and this is used to calculate the corrosion rate. Here are some new specimens before exposure. And these are various types of metals. Here's a steel specimen after exposure in a fairly corrosive system. We perform very thorough analyses of samples. Our lab can test a large number of physical and chemical water quality parameters in many types of water systems. And we have developed some custom analytical methods. The benefits of our lab tests: we give you unbiased third-party results. We can find evidence of corrosion, scale, and bacteria problems. We can determine current treatment levels in a system and which metals are present. And we provide you with a written report, including expert recommendations for remediating any deficiencies that are found. We can also analyze scale and corrosion deposits, which can help determine the cause of a problem and point to a solution. Our ongoing treatment and consulting service develops a custom treatment plan for each of your systems, provides you with instructions for applying treatment and system control charts, and can provide on-site training for your staff to enable them to properly apply treatment and perform regular testing in order to maintain good water quality in each system. One of our field chemists will make a site visit 1 to 6 times per year to make a more detailed evaluation of each system, to test water samples on site, monitor changes that may require attention, and answer any operator questions. This regular service protects systems, can reduce the risk of Legionnaire's disease, predicts serious problems before they occur, and then prevents them, and saves you money on energy, water, treatment chemicals, maintenance, and equipment life. We can detect changes in source water and then take actions as needed by changing treatment plans. We can answer your questions throughout the year and help you with any problems that arise. We can ensure compliance with wastewater permits and regulations, such as the case of limits which would prohibit the use of certain chemical treatments. And if you provide the needed data, we can provide annual water and energy efficiency reports for your facility. Finally, we can perform an unbiased third-party audit of your systems and current water treatment. We will look for potential ways to reduce costs, determine how well the current treatment is working, and be a second set of eyes to discover deficiencies that might have been missed, such as corrosion, scale, biofouling, unsafe recirculating domestic hot water system operation, and degraded testing chemicals. We will make a visit to your facility and gather relevant information about each system. We will test water samples on site and collect any samples that need lab tests in order to obtain more information about the system. We will use the data and sample results to evaluate the current treatment. For State of Illinois facilities, we can recommend chemicals from a state chemical bid list That includes treatments that are often 10 times less than the cost of a proprietary treatment from a private vendor. Finally, we will make unbiased recommendations to mitigate any deficiencies found. Often with a private vendor, there's a real conflict of interest because the person who is telling you how to treat your systems is also selling you the chemical treatment. Typically, a vendor charges little or nothing for the consulting and site visits. However, the income and profit are made through the sale of their treatment chemicals. There is no incentive for him or her to help you reduce your chemical use. IWT does not sell chemicals or equipment, and we do not make money from these sales. We provide knowledge, insight, and solutions with the goal of saving you money through economic, water, and energy efficiency. Contact one of our staff to schedule a site visit to your facility. Thank you for your participation and attention, and I'll now take questions from the audience. Oh, okay. Oh, the question was, how long does a site visit usually take? It depends on the number of systems. So, for an average facility, could be about 4 hours, could be 8 hours for a university or a facility with a large campus. Yeah. In the field, we test water parameters that relate to corrosion and scale, so like pH, conductivity, P alkalinity, M alkalinity, chloride, hardness. We also test for corrosion inhibitors to find out how well the treatment, how much treatment is actually in the system. So we check corrosion inhibitors. We can check some of the scale inhibitors. We can do an on-site test for biological life. It's called an ATP test, adenosine triphosphate. So it's a quick test to check for any kind of bacteria, fungi, algae. It doesn't specify, it just shows whether there's living material there or not. So, of course, we also do visual examination of the water itself, and as we're taking samples, we're right next to the equipment, so we can look at the equipment. We can notice anything that looks out of the ordinary. We can notice leaks. So, yeah. Okay, yeah, the question was, do we do testing throughout the state, and are there size limits on the facilities that we will test? We do have facilities throughout the state, from Rockford to Chicago, Quad Cities, Central Illinois, Southern Illinois, Alton, Carbondale area, Harrisburg, Vienna. So yeah, pretty much north to south, east to west, Champaign, Danville. No, we don't have a size limit on a facility. Yeah, we can do large. We have some large universities that we currently do water treatment and consulting for. Some large high-rise buildings. So there's not a limit on that. Cost will vary with the size of the facility, and especially with the number of systems that need to be tested. Yeah, another point our manager, Mike Springman, brought up is we are completely self-supporting. We do not receive any tax money to do this. So our income is from agreements with various facilities to provide the water treatment service and consulting. the question was, can we give an approximate cost per size of the facility? I guess I'll ask Mike if he has some good numbers. The smallest facility we have is about $1,500 for 1 or 2 visits per year for a few systems. Mm. The largest systems are around $12,000, but they have multiple buildings, maybe 8 buildings, and number of systems in each building. So that's adds up to quite a number of boilers, cooling towers, closed loop heating, chilled water, things like that. Cost depends on, yeah, how many systems need to be treated, tested, number of visits per year. Some places would only need 1 or 2 visits a year. Large facilities, large boiler plants, especially high pressure boilers, should probably be tested 4 or 5 times a year, maybe even 6 times a year.
Okay, thank you very much, Jeremy, for informative presentation. And for those who may have missed the presentation, this will be recorded, so pass the word along to your friends. And thanks.